Thank you all for joining us today, and welcome to the South Central Partnership for Energy Efficiency as a Resource, or SPEARS, policy webinar titled Implications of EER Requirements on Heat Pump Adoption in Texas and Oklahoma. As I told Jonathan just a few minutes ago, I apologize for the not so catchy title, but I think because of the technical requirements and information being presented today, being a little less subtle made a little more sense. I'm Noah Oakes, a state and local policy manager at SPEAR, and we'll be hosting today's webinar. A little bit about who we are. We're one of the 6 regional energy efficiency organizations. We operate in Texas and Oklahoma with the mission to accelerate the adoption of advanced building systems and energy efficient products and services in our region. We do this through several program areas, namely our policy program, our building codes program, local governments program, and our high performance buildings. Our membership includes advocacy organizations, cities, energy service companies, manufacturers like our presenter today, trade associations, and utilities. A little bit of housekeeping. We are offering CEUs today, so if you are interested in receiving credit for those, you'll have to fill out the survey, which will be sent out at the conclusion of today's presentation. And if you've called in on it, you just have a phone number, not a name on Zoom, just shoot me an email, let me know that you want to receive the credits and that was your phone number, and we'll make sure that we can get those squared away for you. We have a couple of upcoming events I want to make you aware of as well. Our codes program is hosting 2 separate webinars on April 25th and April 30th. And lastly, we will have a Q&A session at the end, but if you have questions between now and then, please feel free to use the Q&A function or the chat box, and we'll be sure to queue it into our system so we know that we can get Jonathan to respond to some of those. And so with that, I'd like to welcome Jonathan Moscatello, our presenter today. Jonathan works with Daikin Comfort Technologies, which is a Texas-based company, part of the Daikin Group, a global HVAC manufacturing company. As Daikin's utility relations manager, Jonathan works to connect Daikin with utility industry initiatives while helping utilities connect with initiatives inside of Daikin. Jonathan is a nationally regarded expert in residential contracting and heat pumps. He and his wife, Sarah, founded the Heat Pump Store, a heat pump only contracting business that has installed heat pumps in over 20,000 homes. And as a personal aside, I've had the privilege and honor to work with Jonathan over the last year or so in his current role, as he's been a member of the SPEAR Heat Pump Working Group, and now we'll be working with him as well with the Public Utility Commission's Heat Pump Working Group. And I always seem to learn something new when I talk to Jonathan. So really looking forward to today's presentation, and I'll turn it over to you, sir.
Thank you for the opportunity to speak with you this morning. It's an exciting time to be, a devotee of heat pumps. It's a hot topic in most states in the country right now. And the topic that I want to talk with the membership about today is pretty important for the future of heat pumps. Now, just a little housekeeping. This content was originally presented just about a month ago at the ACEEE Hot Water and Hot Air Forum. So you're going to see the slides make mention of that, but the content is, I think, immediately useful for the work in Texas that we're all involved in. So without further ado, let me tell you about this study. We did some research starting in 2023 to explore how inverter or modern heat pumps work. We wanted to understand if they work as we are designed to make, as we design and make them. Now, when I say modern variable speed heat pumps, I'm speaking about heat pumps that are designed to vary the output. So on a mild day, they can slow down and match the heating or the cooling requirement of the home. But on a really hot day or a really cold day, they actually can speed up all of the mechanical operations and produce more heat or more cooling. And so this represents the state of the art in the future. They are both more energy efficient, but more able to produce comfort for occupants. And so that and a variety of other reasons are why we're focused on this technology going forward as a heat pump manufacturer. Now, we know we make them to operate in a particular way, like the variable capacity programming of these heat pumps. We understand that how they're designed. What we have found over the years is that with particularly people working in the energy efficiency and utility space, that they say, well, that's really cool that heat pumps can vary their capacity and be more energy efficient when they're, operating at a lower end of the range. Do you have any data to help us understand that or to prove that? And I would say in the 15 years I've been working with variable capacity heat pumps, that conversation has happened again and again. And it wasn't until last year that we actually had, as an industry, wide data sets to show or prove how these variable capacity heat pumps work in the field. And so I think what we're going to see today is really our first more public sharing of some of this information. And we are starting to share our understanding of how these heat pumps work on those days that are very hot, towards the extreme of hot weather, 95 degrees. So without that being said, there's the sort of background. Our research is trying to show this in-field representativeness of variable speed heat pump and variable speed air conditioner operations in those EER conditions, which are 95-degree outdoor air temperature and a 75 or so, a basic comfort set point as an indoor. We believe, and we design the heat pumps to operate at a part load. And this means the machines are kind of operating at a lower end of their capacity, not full speed. The EER metric tests the efficiency of heat pumps, but at their full speed operation at that same 95-degree temperature. And as I just stated, we design these heat pumps to operate more at a moderate rate of operation or a low speed of operation. And so what you're going to see today is data that proves that. We'll also speak to some of the specific research questions, like what are the average operational speed during these peak or 95-degree conditions? What is the average part load efficiency? So where are this fleet of heat pumps and air conditioners? What rate of operation or part load efficiency are they operating at? Further, how does it differ from region to region? And then are there any indications of what contributes to the variability that is, obviously going to be present in any large data set? So that is the gist of it about our research study. And I wanted to share real quickly, like, why is this important? Why should you care? Well, in our opinion, as one of the leading global manufacturers, we believe that this modern heat pump is the future. And as America works on expanding electricity supplies and looking to gain as much energy efficiency from heat pumps and air conditioners, we believe that the small side discharge units are better because they rely on the compressor and its computer controls or inverter controls to produce really high level energy efficiency. We can contrast that with the legacy heat pumps and air conditioners, the ones that have dominated usage since really the 70s and 80s, when they became a much more common part of home use. The legacy heat pump is larger on the outdoor, and it achieves that energy efficiency by using much more heat exchanger surface area. So that large cube shape, it represents the heat exchanger surface area. And if you want to make a highly efficient cube shaped or legacy heat pump, you make it really big so that it has a large surface area, and you use a lot of refrigerant. You put more of the fluid or the gas inside, and it will increase its energy efficiency. The problem results is, as we look to heat pumps more and more in this country, and there are states calling for massive numbers of heat pumps to be installed, the legacy heat pump consumes a lot of metal just to make that machine. It consumes a lot of refrigerant. And refrigerant, due to its impacts on global warming, is being regulated to restrict the volume that is produced. And I'll say that again if it's news to you. The refrigerant that's being produced and phased in over the course of the year, the production is being limited on that to prevent, more of this material being out in the world and potentially getting into the atmosphere. So at a time when we're trying to increase heat pump adoption massively, the legacy heat pumps use more metal, use more scarce refrigerant, and because of their size, they consume a lot of shipping resources as well. Contrast that with the modern heat pump, which uses the compressor and its computer controls to achieve energy efficiency. It's a much more small unit comparatively, less metal, much less refrigerant, about half. And then, of course, you can fit much more of them on a tractor trailer or a shipping container. Historically in the US, they've been a premium product. However, in the rest of the world where it's a dominant technology, it's more typical. They're available to consumers, average consumers in every global market where we sell them. So that's the kind of why you should care. That's why we care. So with that being said, let's talk about what we found by looking at the in-field operation. And I think hopefully it'll create a really strong case for why these, modern heat pumps offer a lot to utility energy efficiency program and the like. All right, so we have been able to accumulate a very large data set, over 10,000 systems or sites, and we're looking at operation of those systems during the 2021 season. These are individual HVAC systems, so an outdoor unit, a indoor unit. But because of the architecture of the system, I'll show you in a minute, we've been able to connect those over the home's internet to our cloud servers. That is how we are able to see all of this data. Now, these variable speed modern heat pumps, they often can be called ductless heat pumps. That's kind of how I think they emerged on the market. We're not talking about that kind of a system. We're talking about a centrally ducted system that's typical to most North American homes. So again, just to put a fine point on it, the systems we're going to be looking at, these over 10,000 sites, are centrally ducted systems where there's a modern variable speed heat pump outdoors or an air conditioner. Okay, our study methodology. So we took each of these 10,000 sites and organized them by zip code. Then for each zip code, we associated weather data for that site. And then we started filtering, if you will, to sort out just the kinds of days we're looking for. So our study days are those where the outdoor temperature reached 95 degrees or higher. All other days were excluded from this research. And that allows us to look at more of these peak conditions for which the EER metric was designed to evaluate. The dependent variables, or what we were looking at, was the outdoor temperature at any given time during that day, and then the compressor operating speed. Again, the EER metric assumes that the compressor would be operating at its fullest, fastest speed, the 100% capacity. And our theory or hypothesis was that the compressors on these systems would be operating much less, and therefore providing a significant energy savings. Okay, so let's look at some data. Now, I should pause to say that we started looking at this EER metric because it is a barrier, we feel, to adoption of heat pumps currently due to the federal tax credit having a higher EER requirement, and then the Energy Star certified program having a high EER requirement. There are also utilities around the country that include EER as a requirement for their incentives. And unfortunately, it's disadvantaged to the small modern heat pumps. So we're going to keep going on and researching this subject and looking at a variety of heating, cold climate heating conditions, mild climate heating conditions. We started for cooling conditions at this peak level because, well, it's the most immediate barrier to adoption using incentive programs today. So okay, let's look real briefly at the architecture that we employed to do this study. So as I mentioned before, we had a modern, small, highly efficient outdoor unit connected to some kind of indoor unit, and then what we called our Daikin 1 smart thermostat. Now, we call this a digital or communicating system. And really, because of that system architecture being all really computer controlled, it is able to communicate sensor readings in the outdoor unit, temperatures, pressures, operating speeds, just a variety of variables. Same for the indoor unit. Those are all able to be communicated to this very intelligent thermostat. It's not a a simple thermostat like we've been used to. It's really like a small digital component on the wall. That controller on the wall inside the home connects to the home's Wi-Fi, and then over that interconnect connection, it communicates just really minute by minute data points to our Daikin 1 cloud servers. It's an enormous amount of data. A lot of it is not useful for any of the studies that we plan to do or this study. And so what we've been able to do is just take that enormous amount of data and make it more workable by just streamlining the data on our research servers, where we can then do studies like what we're going to be showing you today. The legacy heat pumps, because they are not digital systems, they don't have sensors, they don't have variable speed equipment and so forth, there really isn't a way to do this kind of work. So I think this presents a really neat opportunity for researchers going forward, because we have very sophisticated digitally controlled heat pumps in homes going in more and more. These are connected to the internet, and so they're available to do research on them, whereas the legacy heat pumps really couldn't do this. So it's kind of an exciting time. Okay, so what did we find through all this work? So what you see here is a graphing of all of the over 10,000 sites around the country on days where that site reached 95 degrees or higher. And so what we did is we created a composite day of temperature, like you see on this orange line on the graph. That represents the average temperature at any given point during its day of all 10,000 sites. Now we selected for those days where the site temperature was 95 degrees or above. So the average for all 10,000 sites peaked at just so happened to be 99 degrees. What you see on the blue line below is the average compressor speed of all of those sites at any given time during that day. And we were excited to find out that just as we predicted or design these inverter systems, the compressor speed changed over the course of the day, but didn't reach the 100% operating speed at the highest temperature of the day. So as we'd expect in the morning hours, where it's comfortable, not all the machines would need a lot, not all the homes would need a lot of cooling. The compressors are operating at a very low rate of operation, just 31% of their total capacity. As the day gets warmer, temperatures climb. In this case, they reach 99 degrees. And our compressors didn't reach 100 degrees like the EER test assumes. Instead, they reached a 74% of their full capacity operating speed. That was encouraging. It's kind of what we assumed. That's how we designed them. But again, we didn't have the data to be able to share until just recently. Now, what's really most useful or interesting about this is that the power consumption is because the machines are operating at a more, let's say, average like set of speed of operation, a reduced speed of operation, the power consumption of the system is more greatly reduced than the reduction in the compressor. And this is what we call part load efficiency. In much the same way that our automobiles going down the highway are very much more efficient at 55, and as you speed to 75, 85 or so, the miles per gallon rate drops very quickly at a greater rate than the speed increase. It's no different for the machines that we're talking about here. They are much more efficient when they're operating at a part load than the 26% reduction in speed that the compressors reduced by. In this case, that 26% reduction in compressor speed represents a 39% power reduction compared to that full speed operation. So we call that part load efficiency. I hope that makes sense. I know it's a little confusing, but it's really exciting. I mean, that represents a significant amount of energy savings compared to what, of course, the EER metric assumes. Okay, so that's a national data set at 95 degrees. Let's look at some regional differences. So in this case, we're looking at the Department of Energy South region. Texas, it falls in the DOE South region. So you can see again our composite day in orange. Just those days represented where the temperature reached 95 degrees or hotter for that day. Now it's not 10,000 units here. I think we were down to about 4,000 units in this geographic area, which represents the South pretty much from Texas eastward, all of those states. So in this case, when it was 95 degrees, the compressor speed average was 77%. So again, at 95 degrees, we saw our compressor speed average peak being 77%. Well, when you consider the part load operation, that reduction, let's say 23% reduction in compressor speed resulted in a 35% reduction in power, again, compared to what the EER metric assumes. So consistent to what we expected, confirms some of our assumptions. Let's look at the Southwest region, a significantly hotter environment when you consider New Mexico, Arizona, Southern California. In this area, it's worth noting the utilities, when we talk to them about EER, say, well, we regularly get very hot and we experience significant summer peak demand challenges. And so EER is important to us. And so, this data set was, I think, particularly important to us because most of the vocal proponents of EER as a useful metric exist in the Southwest. So let's again look at our average day. We have, again, where we get above 95 degrees. In this case, all of those days where we filtered for 95 or above resulted in an average peak of 101 degrees Fahrenheit. So very warm and 6 degrees higher than what the EER metric tests for. In this case, we see a surprising result in that our compressor speed started a little bit lower, and then peaked lower than the South or region subset or the national data set, with a peak of 65% compressor speed at the time when we're experiencing average temperatures of 101 degrees Fahrenheit. Now, that reduction of 45% in the compressor speed is equivalent to a 51% power reduction compared to what the EER metric assumes. So this is a significant reduction and a significant difference in what I think the models that use EER would predict from this product. It's a surprising result, but when we dive into to try to understand some of the why, I think you will, it makes a little bit of sense. So let's kind of pull apart some of this data further by looking at some conclusions that we can make from this. Well, the first result that we found and feel confident about is that large groups or fleets of variable speed heat pumps and air conditioners operate at less than 100% capacity consistently at the 95-degree outdoor ambient conditions. I put the sort of subsets of our findings on that. We can conclude that additional savings from peak load, so peak load reductions, are available for this class of product for utilities or programs to utilize. I think there's additional energy efficiency savings as well from this product, but I think our study simply was looking at these peak demand reductions or peak conditions. So I think our future studies will look at some of the energy efficiency opportunities a little bit more specifically than simply looking at that 95-degree test point. Now, we noticed, of course, that the results vary by region, but as I stated, differently than we assumed. We had assumed that in the Southwest, with much higher temperatures than that 95 degrees, that we would see the average compressor speed increase accordingly. We didn't, and we have some ideas on why that might be. What we found when we looked at other variables within those subsets was that there was an over-representation of large tonnage systems across the entirety of the South and Southwest. So the national data set had an average, let's say, capacity of the heat pumps that was lower than what we saw in the South. And then there were even larger systems in the Southwest. This would suggest that the contractor practice in these regions is to size the machines a little bit larger, or sell, in other words, I'll put that in more layman's terms, like installing larger capacity, cooling capacities at homes in the South and the Southwest. That's kind of consistent with what we see for shipping data that AHRI, shares with its industry partners, that there are more larger capacity air conditioners and heat pumps sold in the South than there are nationally or in the North, for instance. So we think that that explains some of this difference. There are other factors, but we're not as confident in stating them. I think what we also saw in the data are that there are several end user behaviors which contributed to variability in the results. And I think for programs in the future, this points to a real strong need of educating consumers on the differences on how to operate variable speed equipment at its best efficiency compared to what they're used to. So I'll give you an example. I think most homeowners have been conditioned to set back thermostats at nighttime or when the home is unoccupied. This way the systems don't run as often and therefore aren't consuming as much power. It turns out that with variable speed equipment, where the computer system is working to create that efficiency, it's best to set the temperature desirability and only vary it varies like 3 degrees, maybe 5 degrees, depending on the studies that we've seen. And so what we see in the data is when homeowners turn their system on, let's say in the morning before the home or the structure gets very hot, and let the computer control kind of follow, increase its operation through its control and programming, that it allows the machine to stay in control of the heat in the structure and more cruise control, as we say, or operate at a lower rate of capacity. Conversely, or when a homeowner like comes home at 5 o'clock and the system, let's say, had been off and all of the heat builds up into the structure, the variable speed machine is then forced to operate in its highest range or highest speed to try to recover the house and remove all of the heat that's built up in the structure. And at that point, we see that machines, in fact, are operating at 100%. But it's I think really indicative for programs to do a few things. I think there's a case to be made for creating a unique measure or a distinct measure around a variable speed product, designing the savings that it can deliver accordingly, but encouraging any program that operates in that way to make sure you educate consumers on how to get the most savings and comfort out of that variable speed system. So I'm just drawing a little bit of my experience with this product over the years that there's been programs around the country that have identified this as well. So some tips for you there. Now, we have the ability, I would just like to conclude by saying we have the ability to review specific geographies, the data of specific geographies. So if like your utility in a specific part of Texas and you'd like to give us some zip codes and look at how our data set works in your area, in your service area, please get in touch with us if you have an interest in that, because we can we can show you what this means specifically to you and your work. And with that in mind, I want to share my contact info, but also share my colleague John's. He works specifically in Texas with implementers and utility programs, whereas my role is a little bit more with like working with utility regulatory affairs folks or people that work with the PUC on the Texas TRM. So either way, we're both happy to help you. Please reach out to us, and I'm available to answer any questions that have come up in the meantime. So Noah, I'll turn it back over to you and see if we have any questions.
Thank you, sir. So as Jonathan said, we'll have some time for questions and answers. If you want, go ahead and use the raise hand function if you have a question, and we can chime you in. But until then, I just have one quick question for you, I think. You had mentioned some specific metrics being developed at utilities for some of the variable speed technologies. Are there any examples from states that you would like to highlight? Whether it's, I don't think Texas has that yet, but we're working on that stuff with the PUC, but elsewhere, are there other states that you would say are kind of shining examples of this?
We're seeing more and more like a higher tier for products that use variable speed. I think it's typical for a lot of programs to have a ductless heat pump metric. Now, ductless heat pumps are a variable speed heat pump generally. And so while those tend to have some specific use cases, it's noteworthy to say that they have a distinct measure and unique savings. And I think for centrally ducted systems, there might be cause to do the same. Most of what I'm recalling, Noah, is that maybe there's like a higher tier for a central existing home, centrally ducted heat pump. And that higher tier has either the cold climate heat pump requirement or a variable speed heat pump requirement. Interestingly, last year we saw Sacramento's utility, a municipal utility, um, say that we're only accepting variable speed heat pumps, and they had really neat research based on their AMI meters that substantiated that there's just a significant benefit for variable speed heat pumps. And so that's probably the most extreme example of anything that I've seen, but most of the regulated utilities have either a tier for that existing home central system.
Turn it over to Cody with his hand up.
So a question I have for you on the study, where were these systems located? Were they located in a conditioned area, or were they just right in a regular attic area?
It was all over the place. And we don't have that information. Or it's not, I think we could probably, like with AMI meter, you see a certain signature from a certain type of use case. We could probably evaluate that and determine if that indoor unit is in a basement based on some of the temperature and power versus the attic or the garage for that matter. But at this time, we don't know. We don't know if they're in multifamily either for that matter versus, however, we have a best guess based on our contractor surveys that we conduct that most of these are in existing homes versus new construction. So that's about the best I can tell you at this point.
Okay, so yeah, because I was curious to find out how the efficiencies are in whether it's especially out here in Texas or in other places where there's no basements, where it's in a conditioned area versus non-conditioned area, and how the efficiencies differ for that. And I know with Energy Star requirements, you can do ducts in conditioned space, but it's not a mandatory requirement. So I was just curious if they were doing that. If they are putting it in conditioned space, are they getting an extra credit because the efficiencies are higher, and what the difference in the efficiencies between the two?
Yeah, I think, I would say this study's usefulness is that it is large, anonymized data. And so while we lack some of the, maybe you would say, specific ability to specifically pull apart data and look at certain use cases, it does give us a wide geography, a good representative sample to work with. And I think for utilities and programs that want to test the effect of a garage installation, ductwork in an attic versus in the conditioned space, we're going to have to probably go back to the, classic EM and V studies that go on, looking at specific small numbers of sites to get that level of detail. So it's a great question. And I think it's something that, highlights that this metadata analysis that we can offer with this is only one tool in the toolbox. And let's not forget to get into some of the specifics when we need to know more. Any other questions? Don't be shy.
Sorry, I was muted. We have a couple questions here in the Q&A. The first one is, have you looked at how these units perform in the winter and how the variable speed technologies perform during heating conditions?
Yeah, that's being worked on currently, and that's our next phase. I didn't really give much mention to why we started with EER, but it's worth noting that we started with EER because these small area or volume variable capacity heat pumps that are discharge air out of the side versus the cube shaped like discharge out of the top. The consequence of them is that they do tend to have a low EER rating, again, because they don't have that big surface area and refrigerant charge. And so last year when the 25C tax credit came out and the IRA rebate program was announced, which used, again, CEE and then Energy Star certified as the product qualification, the EER requirements to participate were high, which represented a disadvantage or even a barrier for this class of heat pump that we're showcasing today. And so that's why we started with this evaluation. However, we know that most states, including Texas, are looking to get, looking at winter heating with heat pumps, and in particular, getting rid of as much electric resistance as we can. We know this, and so our next study is going to be looking at cold climate operation, and then and specifically how we're avoiding use of electric resistance. It's a little bit harder a study, and to be perfectly honest, a lot of the systems, those 10,000 systems that we saw in this research, are they are probably overrepresented as an air conditioner on a gas furnace as the system. And next, I would say down in a number would be a heat pump with an air handler with electric resistance backup. And I think the study that everyone really wants to see is a heat pump with an air handler and electric resistance. And then maybe followed by a heat pump that switches over to gas heat with a furnace. And for our data, we have probably many more of the first and the second, and very much fewer of that gas. So it's I hope to be able to come back to you like a year from now and share with you some of this heating, similar research, but for heating operation. It's going to take us a little while. It's a little bit harder a study to design, which is, again, making it a little challenging. But great question. We're with you on that. That's the info we want to.
We also have a question here. Has there been any consideration of changing the DOE test procedure to account for these effects?
Well, we're kind of getting there. Our regulatory affairs team is working on that. One of the, it gets a little, like anything in an industry, it gets a little political when you have time, when you have a diverse kind of representation of companies, each with their own particular strategy. One comment I want to make is that what you saw from us with our centrally ducted system today in this research, I think it's fair to say that most of the other manufacturers that make inverter central systems would have a relatively similar outcome. The reason why I feel confident saying that is contractors are contractors. They tend to apply our product similarly to another product. That's number one. Number two is the goals for programming an inverter system or a variable speed system like you saw today are mostly the same from manufacturer to manufacturer. We all have some little proprietary intellectual property in our programming, but the overwhelming majority of it is similar. It gets more down into the nitty-gritty fine detail, and I think some of that is important, but I don't think you would see a massive difference here in this research if it included the great majority of other manufacturers in our space. I would say certainly if you're some of the Asian manufacturers out of Japan and Korea, where they come from a similar climate zone, and therefore the products are designed to work well in that product zone, everything I just said would be true. And so, yeah, I think what we're finding within the regulatory test procedure negotiations is that some of the manufacturers are heavily invested in cube-shaped systems, and their manufacturing is all set up around that. And so they are working to maintain the unique advantages they get today, at the expense of this more sustainable resource, resource conserving approach that we're taking, and others are taking with these small side discharge type units. So we have to negotiate that and work through it. I think in the meantime, there's a lot of, I want to make sure that we want to make sure the markets at least have choice, because we think that we can produce as good a product at a lower price because we're not using as many resources. But if we can get differentiated measures in utility programs, and maybe even some differentiation in Energy Star and CEE tiers, that at least it'll give consumers and contractors the ability to choose a differentiated product. And this will all sort itself out over time if we can let that market choice operate.
Well, I've got actually one more, and it's possibly silly, so I apologize.
Mm.
Has there been any effort? I know it's a probably pretty big lift with the differences in rates, but actual cost savings associated with some of these technology shifts?
It really varies. And I think the number that I can cite offhand is all related to heating, and then using a variable speed heat pump to reduce reliance or eliminate reliance on electric resistance heating. But, excuse me, utility programs that have applied variable speed heat pumps to reduce or eliminate electric resistance see 25 to 50% savings in the cost of heating. I haven't seen the same studies in air conditioning because, again, we don't have these differentiated products and measures. So I'm sure it's out there. I just am less familiar with that because, just my experience working on that heating piece of the heat pump world over the years.
Well, we got maybe one more minute here if anyone has any pressing questions. And again, Jonathan provided his contact information. I'm also happy to provide that if you need it. Feel free to reach out to us as well. But we appreciate it, Jonathan. And if there's anything that we can do to help you out, let us know. And thank you so much for presenting today.
Yeah, thank you for giving us the opportunity, and thanks for everyone for attending. We'll see you around. Thank you.
Thank you.